lecture 24. So in the previous lecture we were discussing the use of a cascode configuration, that is a combination of common source and a common gate stage, or another way of saying the same thing is that a combination of a common source and a current buffer stage in order to increase the output impedance of the amplifier, right? So this is what we saw. Let's sketch both the configurations together and do a comparison. So the original structure that we had was this, right? So let's call this M1 PTD, and we had to bias this, apply an input, and take the output from this node, right? So, but then we saw that the output impedance of M1, right? The output impedance of M1, the impedance looking in, was RDS, which was equal to 1 over lambda IDS. And depending upon what IDS is, and depending upon what lambda is, depending upon what the channel length of the transistor is, we might end up having a reduction in gain, because now on top of this RL, we are getting an additional RDS in parallel to RL, right? So then natural question was to ask, what can we do to increase the output impedance? And then we argued and we saw that one way to increase our output impedance was to put a current buffer, incremental current buffer on top of M1, and that's what we did. So let's say let's call this M1 again. If we call this M2, so we saw that this configuration would have helped, provided of course M2 is also biased in saturation, right? And how did it help? It helped by increasing the output impedance. Here it helped by increasing the R out from RDS to approximately, let's write the full blown, then we'll do the approximate, from R out to from RDS to RDS1 plus RDS2 plus GM RDS2 times RDS1, right? So what was these RDSs? So let's sketch that also. So this is RDS1. So this was RDS2, right? So our R out increased from being a mere RDS to this value. This is clearly sum of the RDSs of two transistors, but that's not the important part. The important part is we were getting an additional term, which is a dominant term, which is the original RDS1, amplified by the gain of the intrinsic gain of the cascode transistor M2. Okay, so this is a useful configuration, and we also saw the requirement of what was the requirement in order to keep both M1 and M2 in saturation. We had to size them appropriately. Also, we needed to apply appropriate voltages at the gates of the transistors. We also saw that since this current in this stack through M1 and M2 is controlled by the VGS of M1, right? To a large extent, it is controlled by the VGS of M1. So the VGS of M2 becomes fixed. So if you change the gate voltage of M2, the source voltage of M2 also modulates accordingly in order to keep VGS fixed, right? So then we from that intuition we could figure out how to bias the gate of M2 just to ensure that M1 and M2 both are in saturation. Okay. Fine. So let's to drive home the point. Let me take some numbers and let's consider this uh, for a few more minutes. So let's say, for example, let's say RDS1. Let's say this RDS for a certain bias current IDS and for certain lambda is equal to 10 kilo ohm. Right? I just pick a number. So let's say RDS is 10 kilo ohm. Let's say RDS equal to 10 kilo ohm. And let's say V0 changes by some delta V, right? So V0 changes from some Poisson V0 to V0 plus delta V. How much do you think the current through M1 will change? And for this case, let's assume that since we are only concerned about the output impedances, let's short the incremental input. So let's assume that V0 goes from V0 to V0 plus delta V. How much current has changed? So this current changed from IDS. This current changed from IDS to IDS plus delta V over RDS, right? That essentially was the incremental current. That is, incremental current is basically incremental voltage divided by the incremental output impedance, and that's what this is. What is the total current here? What is IDS here? Originally the IDS was same in both the branches, but now let's say the output V0 changes from V0 plus delta V. How much will the current change by? Clearly in this case the current will change by delta V over the new output impedance, which is approximately GM2. So this is 2, right? GM2 times RDS2 times RDS1. Correct? So clearly, so in this case, if RDS1 was 10 kilo ohm, and let's assume the intrinsic gain of the transistor was also approximately 10, so this becomes, the total current becomes IDS plus delta V over 100 kilo ohm, right? In this case, the total current would have been IDS plus delta V over 10 kilo ohm. Sorry for the yeah, okay. So from the change in IDS would have been of delta V over 10 kilo ohm. In this case, the change in IDS is from IDS to delta V over 100 kilo ohm. So clearly, you see that there will be a considerable amount of change in the incremental current. This is obvious because this is the backhanded way of saying that the output impedance of our configuration has increased, right? Has increased by a factor of 10 in this case, which is equal to GM2 times RDS. Okay. Okay. So now let's dig deep further in this configuration and see some more interesting things. So with respect to a common source amplifier, what do you think is this configuration certainly gives you a better output impedance, but is there a downside? So what I'm essentially asking is this configuration better than this configuration in some way, or is it only worse? So let's think about from the perspective of the swing limits. Okay, so let's assume, I mean, what is the absolute low voltage that you can bias the transistor M1 in a common source amplifier at? V0 can be as low as VGQ minus 1 threshold voltage, right? So V0 min can be equal to V overdrive of M1, right? What do you think will be the V0 min in the cascaded configuration? So clearly this guy, minimum voltage here, right? So this minimum voltage will be, so let's mark this node, let me call this VS1. So VS1 min is equal to V overdrive 1. Similarly, so what will be the gate of M2? So VGQ2 min will be how much? This will be VS1 min, that is equal to V overdrive of M1 plus 1 VGS of M2, right? So VGS2, right? So what will be V0 min then? V0 min will be V overdrive of 1 plus VGS2 minus threshold voltage of M2, and if we assume the threshold voltage is identical, then this effectively becomes V overdrive of 1 plus V overdrive of. So you see that in the circuit on the left, the minimum output voltage is 1 overdrive voltage of M1. In the circuit on the right, the minimum output voltage is the sum of 2 overdrive voltages, right? Which clearly means that the output you cannot swing as much now as you could have had if you had used a common source amplifier. So the cascaded stage, the extra current buffer, needs some headroom in order to bias itself, and because it needs some headroom to bias itself, you need to budget for that. And what is that cost? The cost is the overdrive voltage of the transistor. Okay, so this is the cost that you pay. Fine. Now the question is, how do I bias? I mean, okay, this is all good that we understand this overdrive voltage. I mean, this is the minimum voltage of V overdrive that we require. But now the question is, what should we do? How should we go about biasing the transistors M1 and M2? Because we have seen earlier that a constant voltage bias has issues, right? It's not a very robust way of biasing a transistor under the condition that the ambient voltages, temperatures, and everything can change. So essentially, if threshold voltage changes, then what happens? So what is a equivalent threshold voltage independent biasing scheme? That's what we are asking. Okay, so let's draw the parallel with common source amplifier again. What was the biasing scheme for our common source amplifier? The current biasing, one of the constant current biasing schemes was using a current mirror, right? If you recall, in one of the earlier lectures where we covered current mirror, or where we introduced current mirror, this is what we had seen. Why was it necessary? This was necessary because note that this voltage here, right? So this is VGS. VGS is equal to what? VGS is equal to 1 threshold voltage plus under root 2 I naught by mu n Cox W over L. if I naught is fixed, right, then what is happening? The voltage of the VGQ, the gate voltage, is adapting itself to the change in threshold voltage. If, for example, the threshold voltage decreases, then VGQ decreases in order to keep I naught fixed. If the threshold voltage increases, right, it keeps it increases VGSQ in order to keep the I naught fixed, right, in order to keep the overdrive fixed. Okay, so in essence, this whatever be the ambient conditions, the currents, the quiescent current on the both the arms will be always be identical, as long as these two transistors, these two mirroring transistors, right, as long as these two mirroring transistors are identical. So hence this is called a current mirror circuit, right. So can we use principles of this current mirror circuit to bias our cascode configuration? Surely we can, and that is what we'll do. So let's start off with how do I bias M1. Assume that we have a current source of I naught available to us. We can do the same thing. We can borrow the same playbook from the circuit on the left. So let's do that. Let's say that I have this is given. So I generate a VGS, appropriate VGS, through this diode connected configuration, right, and feed that VGS to M1, right. So let me call this M3. Okay, right. Let's further assume that what is the underlying assumption? The underlying assumption is that both the W by L's are identical, right. If both the W by L's are not identical, clearly the circuit, when you have same VGS, same overdrive but different W by L, you will have different current, right. So here we are talking about a mirroring ratio of 1, hence we can get by taking a W by L of 1. Okay, fine. So how do we bias M2? How do we bias M2? So what is the minimum voltage that is required, or rather what is the voltage that we require at the drain of M1, not the minimum voltage, but what is the voltage that we require at the drain of M1 in order to ensure that there is perfect balance of current on both sides, right. So so let me repeat what I said. What I'm asking is VS2, right. So what is the required VS2 to ensure perfect current mirroring? So let's think about it, right. So what is our current voltage equation for our transistor? The current voltage equation for the transistor in presence of channel length modulation is of mu(n) Cox VGS minus threshold voltage whole square times 1 plus lambda VDS, right. So if two transistors need to have identical currents, right, and they have same VGS, same overdrive, what needs to be also identical? So this is identical between M1 and M3 because they share the same gates, they share the same source. However, this is not given, right. VDS, we don't know whether they are identical or not. So in order to ensure that the currents in the two branches are identical, right, they are identical to a larger extent than in the configuration on the left, what we need to ensure? We need to ensure that the drain to source voltage of M1 and M3 are also identical, right. So we need to ensure ensure identical VDS also, right? If we ensure identical VGS, if we ensure identical VDS, then regardless of what you do, the currents in two branches will be identical, even if temperature changes, humidity changes, right? Threshold voltage changes, right? As long as the characteristics of the two transistors are identical, as a circuit designer, if you ensure that the VGS and VDS are identical, the currents will be identical, correct? But now we have a problem, right? Who is setting the VDS? Who is setting the drain to source voltage in M3? Clearly, the drain to source voltage of M3 is equal to the gate to source voltage of M3 because drain and gate are connected. So this is VGS, correct? So this voltage is VGS. So how do I ensure what is the how do I ensure VS2 becomes VGS? How do I ensure this? So if I take you back to the previous lecture, what you might have noticed is who is setting that voltage VGS? Who is setting that voltage VS2? Clearly the gate voltage of M2 was setting the voltage at VS2. Why do I say so? Because this current is supposed to be largely constant. This current is expected to be I0 regardless of whatever gate voltage you have. So which gate voltage at M2 that you have, which means the VGS of M2 is constant. Since the VGS of M2 is constant, if you change the gate voltage of M2, the source voltage of M2 will also follow along in the same direction, right? So if we want the source voltage to be equal to VGS of M3, right? So let's say we want this source voltage to be VGS of M3. What will be the expected gate voltage at the gate of M2? Expected voltage at the gate of M2? This will be VGS of M3 plus VGS of M2 for a current of I0. Of course, we are assuming all the currents are I0, and to start off, we are assuming all W by L's are also equal, right? So that's, I mean, when you start off, you have to make some assumptions. We are making that assumptions. Okay, fine. So essentially, where are we at? So let me copy this circuit. Okay, so if we assume for simplicity, it's not necessary, but let's assume this. Assume VGS are equal for all transistors. Right? This is just to make our explanation convenient. It need not be identical, right? So let's assume they are identical for the time being. So which means so that I don't have to write a subscript all the time. So this we expect to be VGS. If this is supposed to be VGS, right, or this is supposed to be, yeah, if this is supposed to be VGS, what is this node voltage supposed to be? This is supposed to be 2 VGS, obviously for a current of I0. Okay, so I need to generate a voltage of 2 VGS now, right? How do I generate a voltage of 2 VGS? Can I generate a voltage of 2 VGS by, let's say, putting a resistor divider? And let's say I have figured out that 2 VGS is supposed to be 1.2 volt. So I put a resistor divider of, let's say, let's say I put a resistor divider. This is VDD, this is R2, this is R1. And I size R1 and R2 such that this is 1.2 volt. Or this is exactly equal to 2 VGS. Will this work? It might work for one particular very sweet case, but it will not work across the variations of threshold voltages, right? Because why? Because note that VGS is equal to what? Threshold voltage plus overdrive voltage, right? So if threshold voltage changes, 2 VGS is essentially equal to 2 VGS is equal to 2 VGS. This is equal to 2 threshold voltage plus 2 overdrive voltage. Correct? So if threshold voltage changes, the requirement of that node voltage also changes. Now if I am making this with a if I am creating that node voltage with a resistor divider as shown here, then we will land into trouble, right? So what is the other option? So let's take a step back again and then see what is the other possible option. So how did we generate the voltage VGS? How did we generate the voltage VGS that was required to bias M1? We generated the voltage VGS by biasing, by pushing a required current I0 into M3, which was diode connected, right? So you have to generate one VGS, right? To generate one VGS, the modus operandi was push the required current into the transistor and have a feedback by connecting the drain and the gate, right? So this is an automatic generation of the required VGS. So how do I generate two VGS? So this is one VGS. I need to put something. I need to put something. So I need to put something here to get another VGS, right? If I put something here to get another VGS, this voltage will be equal to 2 VGS. So what should I put there? So if we see that this two terminal device, right? If this two terminal device is getting me 2 VGS, getting me VGS, if I put the same thing on top, what will I get? So if I put the same thing here, what will I get? What will be the output? Note that what is the current now? The current through this transistor is I0. Hence the difference in voltages between the drain and the source is VGS. Again, the same current I0 flows to the top transistor, assuming both are W by L, identical transistors, same threshold voltage. What is the voltage drop between the drain and the source? This will again be VGS, which means what will be the voltage at this node? This will be 2 VGS. And do you think this biasing scheme is will get affected by this generation of biasing scheme is better than the resistor divider? Of course it is, because our transistor M2 in the original network wants a biasing voltage which changes with the threshold voltage variation in order to adapt itself, and this clearly will serve the purpose, right? So since this clearly serves the purpose, what we can simply do is copy this guy here, so this gives me one VGS, this gives me another VGS, right? And what we simply need to do is to connect these two nodes, right? Okay, right? So this is one VGS, this is one VGS. Let me use a different color just so that we are not confused. If we connect these two nodes, we are good, right? So this is 2 VGS. Always M2 gets 2 VGS, which is what it always wanted. Okay, fine. But let's see, can we do one step better? What is the current requirement in this branch? This current requirement is I0, right? can we generate 2 VGS from the current requirement of this branch? Because see, note that we are already generating 1 VGS. So this guy is generating 1 VGS, this guy is also generating 1 VGS, and we are providing the same amount of current in both the branches, and just that we have put one more diode connected transistor on top to generate the second VGS. So instead of using a separate branch, what happens if I put this guy, put the diode connected transistor on the leftmost stack, we put this guy over here. So instead of confusing you, let me sketch what I am trying to say again, because a picture is worth more than 1,000 words. So what I'm essentially saying is, forget about having a separate branch. Okay. What if we simply do this? What will be this? What will be this voltage? So we know that this voltage is VGS, right? And this voltage will also be VGS, which means this voltage will be twice VGS, and we no longer require the help of this additional branch, right? So we save some current, because now we don't have to use a separate current source. We can get by using one single current source, right? Okay, so now what do you think? Okay, fine. So now the current on the left branch and the current on the right branch will be almost identical. Why do I say almost identical? It will be almost identical because not exactly identical to the nth decimal place, because note that this voltage, this V0, need not be equal to 2 VGS, correct? So this voltage can go, how low can V0 go? How low can V0 go? Clearly V0 min now is equal to 2 VGS minus 1 threshold voltage, right? Which is essentially, if I replace the VGS with threshold voltage plus V over drive, so this becomes 1 threshold voltage plus 2 V over drive, correct? So this is V0 min, and this clearly is, I mean, this clearly can be lower than, and this clearly is lower than 2 VGS. So V0 need not be same as the drain voltage of M2 need not be same as the drain voltage of M4. Since the drain voltage of M2 is not the same as drain voltage of M4, the incremental current, right? So the current in both the branches will also not be identical to the nth decimal place. So if the current here, let's say, is this current in this branch is I0, what will be the current in this branch? When will these two currents be identical? These two currents will be identical only when the drain voltages of M1 is equal to the drain voltage of M3, and also the drain voltage of, so the currents will be identical only when the drain voltage of M1 is equal to the drain voltage of M3, right? So essentially, when this voltage and this voltage are identical, then the currents in both the branches will also be identical. However, the drain voltage of M1 is also affected by a second order, is also affected by, to some extent, by the drain voltage of M2, right? So to the first order it's not, we have been ignoring this effect up until now, but but because we still have that lambda VDS term for M2, right? So the drain voltage of M1 will get affected by the drain voltage of M2, but note that, but not by a significant amount. Had it been a common source amplifier without the cascade stage, right? So the output voltage variation would have directly affected the drain voltage of M1, but in this case it will not affect it as much, right? So even though in this case, so even though EDS of M1 is affected by V naught, we will largely neglect this in our analysis, right? Okay, so this is something that we should keep in mind, because it will help our analysis. Otherwise, what will end up happening is that when you solve problems of current mirror based circuits, you will end up with messy equations with third order terms and all, and that will give you that will make the algebra unnecessarily complicated without giving us too much of insight. So what we will do is we will assume that the drain voltage of M1 is not affected by the drain voltage of M2 to the first order, right? But if we had to calculate, we can still do that because we know the incremental current, right? So what will be the incremental current? The incremental current here will be I naught plus whatever delta I have at the output, delta V, right? Let me use a different color. So it's whatever delta V I have divided by the incremental output resistance looking into the drain of M2. What is that? That is clearly GM2 RDS2 times RDS1, right? So if this is the incremental current, what will be the incremental voltage here? What will be the change in voltage? The change in voltage will be, it will go from VGS to VGS plus this incremental current delta V over GM2 times RDS2 times RDS1 times RDS1, because M1 has a output impedance of RDS1, so these two cancel. So essentially the voltage at the drain of M2 will be the voltage at the drain. The voltage at the drain of M1 will be the change in voltage in the drain voltage at M2 divided by the intrinsic gain of the cascade transistor, divided by the intrinsic gain of M2, right? So this is I understand this is slightly involved. I assumed many things in these explanations, right? But the key thing that you should keep in mind is this statement. The key thing that you should keep in mind while solving your problem is this statement, right? So the drain voltage of M1 in the presence of a cascade transistor M2 is largely unaffected by the swing at the cascade node, swing at the drain of the cascade transistor M2. Okay.